All right, so continuing with the second part of 6.2, this is going to be a lecture on volumes by washers perpendicular to the x or y axis. Now, this phrase perpendicular, when you see or hear the phrase or read perpendicular to the x axis, that just means you're rotating it around the x axis, or perpendicular to the y axis. That means you're rotating it around the y axis. What is this right here? That just means a symbol for perpendicular. Okay, so when I'm writing these problems out, if you see this upside down T, it just means perpendicular. Just like if you saw a couple of diagonal lines like that, that means parallel, right? Like remember when we talked about parallel slopes, you would see that. Why? Because those are parallel lines right there. So remember for the first part of 6.2, we had solids, right? We would get these nice solid like tops or whatever it was when we would take the curve and rotate it about the x or y axis. And they were solid because it was just one curve, right? We had one curve that we were rotating around the x or rotating around the y axis. But when you have multiple curves or two curves, when you rotate about the x or the y axis, you're not going to have a solid shape anymore, right? So not all solids have solid interiors. Some have holes. Oops, that's not it. The wrong hole. Holes or channels. So basically some kind of spacing in between the solid, right? So let's say, for example, we wanted to find the region enclosed by y equals x and y equals x squared rotated about the x-axis. This could have also said, find the region enclosed by y equals x and y equals x squared perpendicular to the x-axis. Okay, so the book, people or whatever, they'll use rotate about the x-axis or perpendicular to the x-axis interchangeably. It just means the same thing. So let's draw a picture of this and see what they're looking for. Remember, it always helps to draw a sketch for these curves, right? Whenever we're trying to find the volumes. So y equals x, we know is just like a nice diagonal line like this. Y equals x squared is a parabola, looking something like that. So we have y equals x, y equals x squared. Now, this problem didn't give us limits, right? Like with the last section is, or I'm sorry, the last part of 6.2, it said, oh, find the shape generated from x equals to whatever point to whatever point, or y equals whatever point to whatever point. Right here, it's not doing that. It just said find the region enclosed by these two curves. So enclosed is pretty much the stuff within them, right? Or where the parts where they intersect. So basically, we're looking from here to here, right? And then it's asking us, what's the shape that's going to be or what's the region enclosed, or what's the area that's going to, or not the area, the volume of this region that will happen, or the amount of it, when we rotate it around the x-axis. So just like we did in the last section, if we were to take, this purple stuff right here and rotate it around the x-axis, it will be semi-top-ish, but think about it for a second. We now have an empty space, right? We have this stuff inside right here. If you can imagine, it kind of be like a weird bowl shape, right? You're gonna have stuff here and stuff here, but all this stuff in between Basically, this green right here, this is empty space, right? Green is empty space. There's a kind of hole or holes that exist between or within this curve right here. Now, how do we find out what this area, not this area, this volume is? Well, it's pretty much like, remember from a few sections ago, we were talking about how do you find the area between two curves? You subtract the upper curve minus the lower curve. Same concept right here, except that now that we're dealing with volume. Okay. So the volume is the integral from A to B of the outer curve, or I'm sorry, pi. We're going to throw that in there, times the integral from A to B of the outer curve squared minus the inner curve squared dx. And really important, this is with this equation here is with respect to x. W R T with respect to x. So what does that mean? Everything in here has to be in terms of x. The limits have to be in terms of x. Your equation has to be in terms of x. Remember, when we say in terms of x, that means it has to be y equals, or y to the first equals the rest of your equation, right? Remember from the first part of 6.2 from the last lecture, we hit a couple questions where we had to rearrange the equation when we were doing it with respect to y, correct? That's the more difficult part of these problems right here. But again, when they say dx, remember everything has to be in terms of x with your equation. So the limits right here have to be in terms of x. The equations have to be in terms of x. Don't forget that right there. So we have outer curve minus the inner curve. But before we even get to this part, we got to figure out the limits, right? Like, what are the limits where we're rotating? Well, it's where these two equations intersect, right? How do we figure out where these two equations intersect? So the limits are found where the equations intersect. Well, how do you figure out where two equations intersect? You set them equal to each other. So we have y equals x and y equals x squared. Since we're doing this with respect to x, we need to have, when we work these equations out, it has to be all in terms of x. So we're going to say x equals x squared. Where did I get that from? Because you're substituting, right? You're saying, oh, if y is equal to x, I can take this and plug it into here. Or you could even take the x squared and plug it into that y, right? It really doesn't matter which equation you plug it into, okay? Now, again, the reason why we have x equals x squared is because we're doing this with respect to x. If we were rotating it about the y-axis, which the rest of the problems are gonna be that because that's the more difficult ones, we would have to rearrange these equations for y, meaning we'd have to say x equals y and x equals the square root of y. And again, that's because we would be doing it with respect to x. I'm sorry, with respect to y. But since it's with respect to x, all our stuff here is in terms of x. Again, when they say with respect to x, you're getting y to the first equals whatever. If they say with respect to y, you're getting x to the first equals whatever. So how do we solve this? Now, you're not going to divide both sides by x. You need to set it to 0. And then from there, we can factor, right? You can pull out a GCF. And we get, from here, you can see, oh, x equals 0. And x equals 1. That's where they intersect right there. So now we have our limits. So far our volume is the integral from 0 to 1, and we have the pi out front. And then it's the outer curve minus the inner curve. Well, the outer curve with respect to x, since we're rotating the shape right here, the outer curve is a straight line, right? So that's y equals x. So we're going to have x, that quantity squared, minus the inner curve. Well, in this case, that's our parabola, or just x squared. So you're going to have x squared squared. Don't forget that, right? And then dx. So now let's go out there and work this out. Let's just apply the squared first. Is x squared minus x to the fourth dx. And then taking an antiderivative is not bad. We still have the pi. This is 1/3 x cubed minus 1/5 x to the fifth, evaluated from 1 to 0. So now you get pi. And then we have 1/3 times 1 cubed minus 1/5 times 1 to the fifth minus the bottom limit. But if I plug 0 in, right? If I plug 0 into both of these terms, you wind up with a big old 0, right? Pretty much 0 minus 0 in this instance, because 0 cubed is 0, 0 to the fifth, 0. So that's all zeros. So all we really have left is pi, and then a third minus a fifth, right? Because again, the bottom limit of the integral is all 0 stuff. So a third minus a fifth is 2/15. So your volume is actually 2/15 pi. When you rotate those specific curves about the x-axis to figure out its volume. Again, leave it in terms of pi, no decimals unless the problem asks you to. But as you've seen for this entire math class, anytime there's pi's or roots, like 99.99% of the time, they want you to leave it in exact form, right? Which is not decimal. So that's how you do it with perpendicular to the x, right? Again, if they're normally not going to give you the limits, okay? You're going to have to figure that out. How do you figure that out? You got to set the equations equal to each other and figure out where they intersect with respect to that variable. But if the problem says find the region generated enclosed by, and they say from like say -3 to 5, for example, then yeah, you're going to use those points as your limits of integration. Now, what about, because doing it with respect to x or perpendicular to the x-axis is not bad. It's when we do perpendicular to the y-axis that's a little more confusing, because we have to a lot of the times manipulate the equations. So I'm going to say volumes by washers perpendicular, upside down t, to the y-axis. So the formula is still the same. It's just that now we're going to have the integral of pi from c to d. So c to d, remember, if you recall from the last section, that resembles the y values of your points. A and b represent the x values of those points. And we're going to have, basically, it's the same concept, the outer curve minus the inner curve. But remember, when we do it with respect to y, instead of thinking outer and inner, because that helps out a lot with respect to x, it's the rightmost curve minus the leftmost curve. So we're going to do it, we're going to call it that. We're going to say rightmost curve and then squared minus the leftmost curve. Squared and then dy. dy right there. Very important, right? So all this stuff has to be in terms of y now. The limits, your equations right there. So let's check out a few. Find the volume of a solid when the region enclosed by x equals y squared and y equals x squared is revolved around the y-axis. So find the volume of a solid when the region enclosed by these two equations is rotated about the y-axis. Well, let's draw a picture, right? It always helps with these types of problems. It just makes it a little easier to visualize what's the rightmost curve and what's the leftmost curve as you're doing that. So y equals x squared, we know that's a parabola, right? That's this. And what does x equals y squared look like? That's also a parabola, but it opens sideways. Now remember a trick that I mentioned to you all, if you're having issues graphing, some equation where y is raised to some weird power besides one, like this, take that equation and solve for y, right? We don't, let's say you don't know what x equals y squared looks like. You have no idea. Remember, if you take this thing and solve for y, you get y equals plus or minus the square root of x. What happens when you graph the positive version of the square root of x? You get this upper part of the green line. What happens if you graph negative root x? Well, the negative in front flips it over the x-axis, so you get the bottom portion like that. So you can always solve those weird y equations with different powers and isolate y or get y to the first, and that'll help you graph it. So, region enclosed. What are we looking for? This, right? We're taking this now, and we're not rotating it about the x-axis. We're taking it and we're rotating it about the y-axis. So if we take this and rotate it about the y, right, through the y-axis, it'll look something like that, right? And again, we're going to have some empty space stuff, right? All this stuff in between is empty space. That's what we mean by washers, right? Remember, a washer is just like a disc with a hole in it, right? So yeah, remember we basically have an infinite amount of washers with various diameters increasing up, but they all have little holes in them, right? Because there's empty space in between. And that hole gets bigger and bigger and bigger if you were to keep expanding upward and onward. So how do we figure out the volume? Well, remember the formula says it's pi, and then we need these limits, right? C to D right here. C to D. Those are the y values, right? Like, where does this intersect here and here with respect to y? So where does the curve, or do the curves intersect with respect to y. So how are we going to do that, right? Now be careful. This is the part where the people start screwing stuff up because they just look at the original equations, x equals y squared, y equals x squared, and they just set them equal to each other in their current form. Well, you can't quite do that. Remember, if we're doing this with respect to y, both of your equations need to be in terms of y. That means you have to have x equals blah, 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 right? Like this one is okay because it's x to the first equals blah, blah, blah. This one is not okay because it is x squared equals y. So we need to isolate x in both equations. Again, x equals y squared. The original for this one is okay. This one right here. So I'm going to say this is equation 1 and 2. If you need to label that, 1's okay. What about 2? Is the second equation in terms of x? So we have y equals x squared. It is not, right? We need to take this and isolate it for x. How do you do that? We take the square root of both sides. So you get x equals plus or minus the square root of y, correct? Don't forget, whenever you do that square root property, you have equations, you have the positive version and the negative version. But there's two equations right here. So you may be thinking, well, which one do we use? Do we use plus root y or do we use negative root y? Well, look at your sketch. Where's this green region at up here? It's on the positive y. So we're going to use the positive square root of y. If your curve was down here that we were analyzing, down here, where y is negative, you would use the negative version of that. So you got to pay attention to that right there. So we need x equals square root of y. And again, it's because we're shading above the y-axis in the positive region of the y-axis. So now that we have that, we have x equals y squared and x equals square root of y. We're going to set these equal to each other. Remember, you're substituting. It doesn't matter which one you plug in, right? I can take this y squared and plug it into here, or this square root of y and plug it in for that x right there. It's the same thing, okay? It doesn't matter. You're going to get the same answers. So I'll just take this and plug it into there, y, because x is equal to y squared. So if I have y squared equals square root of y, how do we solve this right here? Well, we have to get rid of, first of all, probably should get rid of the squared, right? Should do that right there. How do we do that? We're going to square both sides. So we have y to the fourth equals y. And then I need to set it to 0. So we have y to the fourth minus y equals 0. And then from here, what do you do? Well, we're going to factor again. We pull out a y, and then we're left with y cubed minus 1 equals 0. So now you have y equals 0, right? And then you have y cubed minus 1 equals 0. Well, here's one of your answers, 0. This one, when you solve it, right, you get y equals 1. 1 cubed is 1 minus 1 is 0. Or you would add 1 to both sides, take the cubed root of both sides, and you'd still get 1. So those are your limits. So we have the volume is equal to pi. And then from 0 to 1 of, now remember, when you are rotating or finding the volume when rotating about the y-axis, it's the outer or rightmost curve. I know the book will say highest curve or outermost curve, but it helps to think better in terms of rightmost. So what's the rightmost curve here? Is it the parabola or the square root that we had? Or is it, which one is it going to be? Well, it's this one. This is the rightmost curve, this. Now, what is that right there? That is y equals x squared, right? But be careful though, right? Be careful because this integral is in terms of y. So you can't use y equals x squared. You got to use square root of y. So it's going to be the square root of y squared. That's your rightmost curve right here. Again, I'm going to repeat it. This is the part where people mess up when they are doing it with respect to y. They gave us this equation y equals x squared. That's the rightmost curve. But because we were integrating with respect to y, we had to use this equation in terms of y, meaning you have to have x equals by itself. That's this. Remember, we solved this for x, so that's why we're using square root of y. And then we're squaring that because it's always the function squared when finding the volume. Don't forget that. If it's dy, all your equations have to be in terms of y, meaning x equals whatever. X to the first equals whatever. X squared equals y is not all in terms of y because you have x squared. You needed to get that to an x to the first. And when you do that, you got this, right? We worked it out off to the side. So that's your rightmost curve minus the leftmost, that's the green, right? What's the green one right here? Oh, wait, hold on. No, that's right, yeah. So what's the leftmost curve? It's the green curve right here. What's the green curve? That is the x equals y squared. So we're okay with that right there because again, when we say dy, everything's got to be in terms of y. In terms of y means x to the first equals whatever. So that's our leftmost curve. It's the y squared. So you're gonna have y squared and then dy. So rightmost curve, that was the parabola y equals x squared. But remember, since we're rotating about the y, it's got to be in terms of y, meaning we have to have x to the first equals something, which it wasn't, right? So we had to take this y equals x squared and solve for x. And in doing so, we got the square root of y. Leftmost curve, that's this one. That was that was x equals y squared. That one was already in terms of y, right? Because it was x the first equals whatever. So that's where these two are coming from. So now we can go out there and solve it. Let's apply the square first. This is just square root of y squared is y, and then minus y to the fourth dy. And then now we have, when we take the antiderivative, we have a half y squared minus 1/5 y to the fifth, evaluated from 1 to 0. So your volume, again, is the upper limit minus the bottom limit. Your bottom limit is going to be 0 minus 0 again, right? Why? Because we just have zeros right here. If we plug it in, that's why I put 0 minus 0. But it's not always going to be that, right? If this is like -10, you'd have to plug -10 in and evaluate it. So what do we have right here? We have pi, and then a half minus a fifth. That's pi. And what is this? Is 5/10 minus 2/10. So you get 3/10 pi. That is your volume right there. So let's try another one of these with respect to y, because the x ones are not bad. We're normally used to dealing with that right there. But again, it's just manipulating these equations, figuring out the limits when you are rotating about the y that people have troubles with. All right. Let's say this time we have these two curves. So we're trying to find the volume generated. And I'll say B slash TB between y equals x and y equals square root of x when revolved around the y-axis. So conceptually, what's going on? We have this straight line. We also have square root function. This is y equals x. Green line right here is y equals square root of x. And we have x and y. So if we were to take the region that was enclosed, right here, it's basically this stuff. So we're trying to find this, right? If we were to take it and rotate it about the y-axis. So something like that, right? So if you want, you can figure out what's the outer curve first, or the rightmost and the innermost. But can we do that right off the bat right here? No, because there's a problem. Since we're doing it about the y-axis, right? We're trying to find this volume about the y-axis. All your equations have to be in terms of y. Not all of your equations are in terms of y. Are both equations in terms of y? The answer is no. So the first one, y equals x, that's okay. The second equation, y equals square root of x. No, it's not. That's not in terms of y. Remember, what does in terms of y mean? It means that your equation has to be x to the first equals whatever. This one's okay because it's x to the first equals whatever. This one's not okay because this is not x to the first equals whatever. So we need to take it and solve it for x. How do you solve this for x right here? You square both sides. So now we have x equals y squared. This is the equation that you're going to use. Like that's your new, or we'll say modified 2 equation. 1 did not need any modification. It was already in terms of y. Why is that? Because it was x to the first equals whatever. Why is equation 2 not in terms of y? Because it's not x to the first equals whatever. We had to put it as x to the first equals whatever. So remember that. Now from here, where we're going to go, we can figure out where they intersect, right? Remember, we have to figure out where they intersect with respect to y. So we have y equals root x, have that. And I also have x equals y squared. Remember, why am I using this equation? Because this is in terms of y. That's this, right? Just dragging it along. And then, of course, you're going to substitute. Doesn't matter which one you plug into what. Y is equal to x. Say I wanted to take this and plug it into here. Or I could take the second equation, substitute in the first. It doesn't matter. If you plug this into this, you get y equals y squared. Again, you set it to 0. You get y squared minus y equals 0. Then we can factor. Remember, anytime you have a variable with a power higher than 1 and you're trying to solve it for that variable, you have to set it to 0. So we get y equals 0 and y equals 1. So we have our limits. So in this case, what was the rightmost curve? I shouldn't have erased it, but what was it again? We had square root of x and y equals x. Yeah. So what was the rightmost curve right here? The y equals x was correct. That's the rightmost curve. That chunk right there. So that's your outer curve. So remember, it has to be in terms of y, meaning x the first equals whatever. That's okay. So it's just going to be y squared minus the leftmost curve. Well, the leftmost curve was initially, what was it? I erased it. Y equals square root of x, right? It was this chunk right here. That was the leftmost curve, but that was not in terms of y. We had to take it and solve it for y. Remember, in doing so, we got x equals y squared. So we're going to use that. So rightmost curve minus leftmost curve. And again, everything is in terms of y. Your equations are in terms of y. Your limits are in terms of y. So we apply the squared, we get y squared minus y to the fourth dy. Then this is 1/3 y cubed minus 1/5 y to the fifth. And then we have pi out in the front. Evaluate from 1 to 0. So now we have pi, and you have a third times 1 cubed minus 1/5 times 1 to the fifth minus the entire bottom. Again, that zeroes out. So we have pi and then 1/3 minus 1/5. This popped up before. That's just a coincidence. I don't know why all these problems keep rigging out so that it's always something like this. It won't always be a third minus a fifth, okay? So if we multiply that out, we know that it's 2/15. So it's 2/15 pi. Or not multiply it out, but compute it out. We get 2/15 pi. All right, so let's do another one, right? Another with respect to y. So let's say this time we have y equals x squared and y equals 2x. So we want to find the volume again, right? Find volume when rotated about the y-axis. So again, rough sketch is this. Y equals 2x is still a straight line. It's just rising a little faster. But it'll look, something like that. And again, we're going to have we're not focused on this stuff right here. We just want it where it's enclosed. So we want this purple stuff, but rotated about the y-axis. So you want this. Everything always looks like a bowl. But this has empty space in between. Now, of course, we got to find the limits, right? All that stuff. But because this is about the y-axis, everything has to be in terms of y. Are these equations are both equations in terms of y? So we have 1, y equals 2x. Is that in terms of y? No. Remember, in terms of y means it has to be x equals something, which it isn't. So if we get this and solve it for x, you get x equals basically y over 2, right? Because you're just dividing both sides by 2. That's the equation that you would use right there. What about the second one? Is y equals x squared in terms of y? Meaning, again, is it x equals something? No, because you have x squared equals something. How are we going to get x by itself right here? You got to take the square root of both sides, right? So you get x equals plus or minus square root of y. So you got two equations. Which one do you use, the positive version or the negative? Well, because it's opening upward in the positive part of the y-axis, we're going to use the positive version. So we use root y. Again, if it was opening downward in the negative y region, right, the third or fourth quadrant, you would use negative root y. So now we have our two equations, both in terms of y. Again, why are we having to solve these right here for x, or put it in terms of y? It's because we were asked to rotate about the y-axis. If you were asked to rotate about the x-axis, you just use these two equations. Why? Because when they say in terms of x, that means y to the first equals whatever. Y to the first equals whatever. You'd be good to go. So now we need to figure out what are the limits, right? Limits of integration. Well, you got to set these equal to each other, right? We have x equals y over 2. You also have x equals square root of y. And again, it doesn't matter which equation you substitute into the other, right? You're going to get the same result. So I'll take the right one, for example. I'll take this and plug it into here, just to show you. It really doesn't matter. They're both solved in a similar fashion. If you do that, you get square root of y equals y over 2. Now, how are you going to solve this for y? Well, you have this y trapped inside of the squared. We got to get rid of that squared to get to that y. So you're going to square both sides to start with. So when you do that, you get y equals y squared over 4, right? Got to square the denominator. Don't forget that. And then we keep solving, right? Well, I got to move the 4 over. So I'll multiply both sides by it. We have 4y equals y squared. Set this to 0 because we have a y power higher than 1. So we have y squared minus 4y equals 0. We can pull out a y. So we have y times y minus 4 equals 0. And you get y equals 0 and y equals 4. Those are your limits. So far we have the volume is pi and the integral from 0 to 4. And what's the rightmost curve in this case right here? Well, it was the y equals the x squared, correct? But because we're doing everything in terms of y, it has to be the equation x equals square root of y. Where did that come from? Because we took y equals x squared, remember, and we solved it for x. So it's going to be square root of y squared. That's the rightmost curve minus the inner. That was a straight line. But we're not going to use 2x because, again, this equation was not in terms of y. If you solve it for x, you got y over 2. So we have y over 2 squared and then dy. All right, so let's apply that squared first. So the volume, and then we're going from pi, and then from the integral from 0 to 4 of just y, because the square root of y squared is y, minus, I'm going to say 1/4 y squared dy. But don't forget, you got to square the bottom. I just pulled it out as a fourth. You could have left it as y squared over 4. It's the same thing. Now let's go out there and integrate. So this is a half y squared. This is And then if you want, I'll leave it as this minus 1/4 and then 1/3 y cubed evaluated from 4 to 0. And yes, you can multiply this in, right? This is just 1/2 y squared, or actually I'll plug the limits in. I'll say 1/2 and then 4 squared minus 1/4 and then 1/3 4 cubed minus the bottom limit. So this all zeroes out, right? But I'll fill it in like this. So we know that this all goes to, that's just a big fat 0 right there. What about this stuff? So 4 squared is 16, half of that is 8, minus, now right here you may be wondering, oh, why didn't I multiply the 4th then? Well, because I saw that this 4 would reduce with one of these 4s, right? You could have said, oh, 4 cubed is 64, 64 over 12. Or you could say, oh, look, there's a 64 up top. There's a 4 on the bottom. I could just knock out one of these 4s because 4 cubed over 4 is 4 squared. So that's 16. So we actually have 16 thirds left over. And this is pi, and this is 24 thirds minus 16 thirds. So you wind up with 8/3 pi as the volume. So again, really important, the mistakes that people make with these problems rotating or finding volumes is when it comes to the y-axis. Remember, your equations have to be in terms of y. That means x to the first equals whatever. And then the limits right here have to be in terms of y. How do you find out where the equations the limits, you set the equations equal to each other, but you have to make sure they are in the right variable, right? With respect to x. When they say with respect to x, that means you're rotating about the x-axis. That means your equations have to be y to the first equals whatever. If you're rotating about the y-axis, that means your equations have to be in terms of x. That means x equals whatever. Okay, x to the first equals whatever. All right, so make a note of that right there. And of course, with the limits, don't forget that. All right, I keep repeating it. I've probably said it like 50,000 times in this one little recording, but that's the parts that people mess up on, and then that's why they get the problems incorrect. They set up one part of it correctly, like they'll set up the equations correctly, but use the x limits right here when they're supposed to use the y. And they will always tell you where to rotate. They will specify about the x or about the y axis. You'll never have to guess that right there. Okay.